Take it away.
All right. Hi, everybody. I'm so excited to be presenting to all of you today. My name's, as I introduced myself, my name's Sol. You probably know Nolan since he goes to Wilson. We were both students in 2020 at Wilson High School, as well as participants in the 2020 virtual Pine Mountain virtual astronomy camp. It's a annual tradition for our science department wherein a group of upperclassmen get to do a practical astronomy with a senior group of mentors. You're probably somewhat familiar with that. And the fact that this year our camp was done virtually with students working from home and our mentors working online. Nolan and I worked under Mr. Richard Barry, and our investigations over our 2 weeks of camp concerned variable star XX Cygni. We've got a lot of fantastic findings and results, so we might as well get started. Next slide. So to start off our inquiry, we had to look at what had already been done. Of course, there have been many studies of XX Cygni over the past 116 years since the star was discovered. Reading and reviewing the historical work of others helped us prepare to design our own investigation and find what questions we can personally help answer. We've learned to read academic papers thoughtfully and critically over time, as well to extract meaningful information. Quite a few of these papers we used for reference. On top of literary sources, we also had the privilege to talk to Dr. Michael Joner and Dr. Ann Gusick when we were writing, when we were in the process of PMO, about our research, and we got to ask them even more specific background questions about XX Cygni. Their help was essential in providing us with this depth of understanding that we have now. Next slide. To kind of catch you up a little bit on XX Cygni, it is a Delta Scuti variable star in the Cygnus constellation. It's classified as a metal poor, high velocity, blue-white population 2 star, and is characterized by its unusual single mode pulsation, large amplitude, and long period for a star of its class, which that's the reason, all those words that I said, that's the reason why it's interesting. Photometric observations of the star have also revealed there are period changes that are positive, which is unlike other SX feed classified stars. So we thought it would be worthwhile to look into the pulsation behaviors of XX Sig with extension and greater precision in order to confirm a relationship between period change and stellar evolution. Next slide.
So as Sol talked about, the study of the star has been really historic, over a century. And technology has come a long way since the star was first studied. So when we said on that slide that the studies were inconclusive, it wasn't any fault of the scientists, it was simply technology. So now we're lucky enough to have CCD, photometry, cameras, all that we can use to make very precise measurements, to learn more about the light curve and to make better observations. When the star first was studied in 1904, they actually would have these giant tubular telescopes. Well, I suppose all telescopes are tubular, but these giant tubes that would project images onto film, and they'd have to wait for those images to develop. And it would take time away from actually being able to take another image. And so it was a lot less refined than it is now. And that allows us currently to take a lot better data. So when we set out, we wanted to use that advantage and try to clear up some of the past inconclusivity. So let's look at how we got that data. It all started in Alpaca Meadows Observatory. This is Richard Barry, our mentor's personal observatory. If you're curious, he's using a Roe Ackerman Schmidt telescope with an 8 millimeter refractor and an Eta Horizon camera. It was here that we took about 2,000 images each night, rolling from dusk to dawn. And in total, we took about 20,000 images. This is just one of them. And at first, to me, it just looked like a bunch of dots on a screen with some gray noise in the background. But It was my job to process images and get data out of these dotted pictures. So I had to make sense of them. And I started with that bright triangle of stars in the center of the screen. I would draw a line across that hypotenuse. Then I would extend that line all the way to the next bright star, draw an obtuse angle to the next bright star, and then split the difference between that first star and the second one, essentially the bread of the sandwich. And then the turkey, the contents, is XX Cygni. The reason why I use the sandwich method is because those two stars that I referenced, the bread, are actually important for image processing in other ways. They're called the comp and check stars. So here's the interface of the image processing that we used. It's called AIP for Windows, Magnitude Measurement Tool. Cool enough, Richard Berry actually, I can't remember if he made the whole thing or was an instrumental part of it, but he definitely knew his way around the software because he made a lot of it. But the star with a V next to it, this one right here, if you can see my mouse, that is XX Cygni. That's V for variable star. The blue circled stars are our comp and check stars, which we use to reference against Cygni to try to rule out any sort of possible error. If there's a cloud passing overhead, it can kind of compensate for that. And then the rightmost star with a yellow circle around it is what's called our guide star. And that's where humans need to monitor it. So when I did image processing, I would spend a couple hours just kind of staring as each of the 2,000 nights worth of images, or 2,000 images from each night flashed across the screen. But occasionally there would be a swarm of SpaceX satellites, some blurring, something like that, and there would be a problem. And computers, unfortunately, aren't smart enough to fix that problem. So I had to click on the guide star to make sure that everything was still calibrated and where it should be. If you're interested in the specs of our camera and all that, they're right, and the way we process images, they're right there. So once we had each of our images processed, we'd put them into a text file and then move them over to Excel, and it would look something like this. The most important columns being B and C, that's where we extracted what we actually took data on, which is the time and the brightness. Now, one funny thing about this is that this is 31 rows long, but we would have we would have 2,000 in total. So it was a lot of data to process, and fortunately, we have computers that allow us to do it at the click of a button. As I talked about with those important columns, the two things that we looked at were time of maximum. We did that in heliocentric Julian days because that's sort of the convention of astronomy, and stellar magnitude, which is, I don't know if we've been over it, but it's a reverse scale. So the lower the magnitude gets, the brighter the star is. So looking at those or keeping those in mind, we'd blow up I think it's the top 250 data points, everything above an 11.8 magnitude, or I suppose below, if you want to look at it that way. And we would do what we called the quick and dirty method, where we follow pixel steps up to the peak. That would be the peak brightness, because we actually inverted the graph. So we'd follow the pixel steps, find the graph that's right about here, and then like I said, it was quick and dirty. So we look for something slightly to the left. It's right about here, and slightly to the right. And then we'd average them out. And that would give us our time of maximum. And then we could plug that into the graph to get the actual X value. Y value, the magnitude. But that's not the best. It's quick and dirty. It doesn't really pass in the peer reviewing process to just say, yeah, we actually eyeballed it. So we later worked on something that in Excel, by manipulating the decimal places, I think we had it out to 16 decimal places or something. Excel was able to spit out our time of maximum and magnitude automatically, which made things a lot easier and more defensible, as we didn't have to say that we eyeballed things. So that's just an example of what we did later. And currently, I have to plug this because this is sort of my baby, my project. I'm coding a new data analysis tool that we can use in RStudio, which is an object-oriented programming language that allows us to get the time of maximum, the brightness, but then also do a couple statistical things like getting rid of outliers and snipping points at the sides to ensure that we have the cream of the crop of data. So you can see the images on the right are sort of what's going on with the data processing, where we're looking at a scatter plot of the residuals. That's how well they fit, getting rid of outliers. And then that box plot shows you If you remember your box and whisker plots, everything on the outside of the whiskers are actually outliers. So the code gets rid of those iteratively until we have no more. Now I'll pass it over to Sol again.
Yeah, all right. So okay. Yeah. Um well, okay. After we've transferred the raw data to Excel, it's time for analysis. We first take the data extract it from the FITS files and move it to Excel, where we can tabulate it and pretty basically analyze it. The most essential of these values we record in the time of maximum time of maximum magnitude in the unit of heliocentric Julian days. We compare our observed values to a computed or theoretical time of maximum calculated by using the epoch. So in this column, there's the heliocentric Julian days maximum magnitude. And then Nolan, the next one. Then the computed one, the theoretical time of maximum. Then we compare these two values and we call that the O minus C. And there's a linear comparison of them and then a quadratic comparison. And then we can determine whether the maximums are occurring before or after they're supposed to, therefore letting us know whether the periods are decreasing or increasing. Next slide. So this is our data with, oh shoot. This is our data with all of the historical data all lined up in one. You can see the historic data is in blue, the AVSO, 50 or so data points from the AVSO database in green, and then the PMO, the data that we've collected in red. So using the linear ephemeris, sorry, using the linear ephemeris, you can see that there's definitely a change in the expected time of maximum. This is even more obvious though when you get to the linear, the quadratic ephemeris though, which is in the next slide. This is okay. Sorry, I need to get back on track. Okay. This is just our data using the same O minus C scale as before, but it kind of shows how, like, so on the y-axis is the O minus C, which is remember the difference between the expected and the actual time. You can notice the scale on that is so very tiny, so close to zero, and then the cycle number. So what we observed in our time was that the observed and the calculated were so small. And this, like, it's really what's astonishing about what we found is that how very small these, how exact our measurements were. We're talking about things on like a star level. The times of maximum that we find have a span of plus or minus 0.005 days or 7.2 minutes. In the span of time that we measured 40 days, and the standard deviation is 0.00024 days or just 22 seconds. So really what's impressive about all of this is how exact our measurements ended up being. Next slide. So this is the 18-year time span of the exact same O minus C scale as before. So over on the far right side, you can see our data. It's all clustered together. And you kind of like what Nolan was talking about before, all like historical data has had a lot more discrepancy between standard deviation a lot different from 0. So this is probably why people thought that there was some period changes going on, because there was all sorts of wacky measurements going on. But you can see like measurements all over the graph, except for our data, which is just this neat little clump right there on the end. And so I think maybe, is there one more slide? One more graph? Yes. So to wrap up the graph portion, this is the same as the first graph, but using the quadratic ephemeris. So this is all of the historical data, but just on the quadratic ephemeris, you can tell that like the data goes all over the place, except for our little data right at the end is all neatly clumped together because our measurements were so nice. And we've used this data to prove that since the ephemeris is consistent with a continuously lengthening period, over time, the observed times of maximum will fall a bit late. So the O minus C is continuously about the same, meaning that it's continuously, I think that would mean it's a little bit positive each time. So it's the time of maximum falls a bit late, if that makes sense. Math. Next slide.
All right. Yeah, I think what's super cool about those graphs, Sol took the deepest dive into those, so he understands a lot more of the nitty gritty of them. But what I think is super cool is just looking at them. I don't always learn through reading. I really like looking at images. So I've got a couple images here of our data as a whole that just shows, I suppose, what it looks like. Here's a program created by the American Association of Variable Star Observers called VSTAR. And what we've done here is essentially take all of the 20,000 images that we've taken, whether it's in twilight with clouds passing overhead, SpaceX swarms, anything like that, and chunked it all into one light curve. And it's pretty remarkable how little the spread is. But I also just think it's super cool to have a look at all of these different patterns that have been overlaid. Each, this is multiple nights worth of, it's 20,000 images, but all of these layer up to create this very concise story. Another thing to note is at the very bottom, we can see a little ripple, and that lends itself to an overtone, which is really interesting when you look at how variable stars work, or stars in general. They've got different envelopes of gases where there's, I don't even understand half of how they work, but they're expanding at different rates, which changes not only their temperature and brightness, but how the brightness shows through. So there's a lot of complexity here, and not everything's moving at the same speed. So if we look at that frequency, the highest peak, it's just over 7. That would be 7 times a day, which lends itself to about 3.14 hours, which is the period of XX Cygni that we know. But there's also one at about 14.9, a little bit higher, which means that there's something else complex going on within the star. Just in my opinion, that's so cool to see. This giant burning ball of gas so many miles away is doing these complex things, and we can actually observe them and see them and visualize them.
So what's like to conclude, just over the course of 2 weeks, we were able to document 23 times of maximum light with extremely accurate precision, with remarkably small error. The differences recorded on the same night are within fractions of seconds of each other. And yeah, it's pretty incredible that we were able to do all of this over like virtually, with Richard communicating, never actually meeting in person, with the resources of Pine Mountain. We conducted a experiment of scientific value, testing some like high caliber, doing some high caliber science of high cadence imaging, learning how to do polynomial curve fitting, and to boot, our results are so consistent and more accurate than commonly used methods, we got to present to the AAVSO monthly meeting and annual meeting to a crowd of, I think our biggest was definitely over 400. And we might even get to write a paper about it, about the fact that we find no support for advanced or delays times of maximum light. Next slide. There might be some questions that still remain. The first one we kind of have an idea of, would results be slightly different if we used a photometric filter? Because our mentor, Richard Berry, just did research in 2009, looking at XXSig with a photometric filter, and he didn't notice anything particularly different about it. But these other questions are still ones that remain. Obviously, there's a lot of things remaining about the star that could use further research. So that there's always more research left to be done for someone already in the field or somebody in this group right now. Next slide.
So to zoom back out, I like to look at the trajectory of our project as a whole. So of course, we started with planning, gathering data, and we even did a presentation in the process, but we also formed conclusions. And all of this was in the past. We're sort of in this stage where we're trying to get things ready to publish as a paper and make sure that we're looking at solid data, making sure that our conclusions are where they should be. And we're doing that by, I'm continuing to write that program. We're looking back into the literature, and we're making sure that our methods are solid. Because in the future, we're actually going to be publishing at least one paper on this, potentially two, just about our methods and then the star as a whole. But if anything, this goes to show that a virtual Pine Mountain Observatory does not meet anything. In fact, I think that this is an opportunity that couldn't have happened in an in-person Pine Mountain Observatory. So if you ever, I don't know, getting down that things are all online, there's really a lot of potential to do more, because Pine Mountain Observatory, I believe, is usually 3 days, but we got 2 weeks and all of the time on top of that to stay in contact and present to the AAVSO and all of this. So it's really exciting, and don't get your hopes down if Pine Mountain Observatory is online this year, because it is really still a special opportunity. So on the note of special opportunities, we'd like to thank all the people that made this possible. Of course, our mentors, some of the people that we talked to, astrophysicists and researchers, of course, Mr. Minato for putting this on and putting us onto this experience. And we also worked a lot with the American Association of Variable Star Observers to present our research. Here are our references if you're just fixing to try to, I don't know, find mistakes or anything like that. But if not, we're all set, and I suppose we could take some questions.
Or read more about it, actually.
That would be a better way of putting it.
Because I had to read all of these papers, and you know, if you want extra credit work, you can too.